Okay, now we're going to look at example 5 in the class notes. And one of the ideas here is that while the particle motion you should be very familiar with because we've done a lot of work with particle motion problems in example 4, although the new thing with the particle motion problem is now we're including the integrals and the how we're using the integrals as net change into the problem as well as understanding all the component parts of how particle motion works. But we can accumulate so many other things other than your velocities and distances. So what we're going to be looking at is this idea of using a rate function to describe how a quantity of something changes. And then the integral will give you the net accumulation of whatever that quantity is. And so we're just going to keep reminding you that what you have at any given moment is a combination of how much you started with plus how much you've accumulated since then, your net change. So we're still using that kind of idea that f of b, what you have at any given moment, is what you had when you started plus the net change from when you started to when you ended. Okay, so it's the same idea, but instead of having, say, a position function like s of t be what we're talking about here, we could be talking about a quantity of something. All right, so let's take a look at example 5. And I believe we've seen example 5 before because I've used parts of this either on a test or the exam. I can't remember exactly where I've used it, but we've seen it before. So the beginning part of it should be fairly easy. So we're going to do the same thing. We're going to go through it. We're going to create a strategy for you guys that I would like you guys to go and work the problem and then come back and check your answer with the key. All right, so notice that while in example 4, we were given a graphical representation. So you were given a graph and then you were answering things from that. Here in example 5, you're given the numeric representation. We're given a table of values. And we're going to be using the table to help us answer the questions. All right, so let's read through the question and see what they're asking. So we have a zoo that sponsored a contest to name a baby elephant. And the zoo visitors are depositing entries into a special box. So what we're looking at is a function that is going to tell us the quantity of entries in the box t hours after noon. And so this right here, E of t, is the quantity function that we're looking at, okay? So this is like your original function. This is not a rate function. This is your original function. And then we have over here, and we're doing it between noon and 8. So again, setting up this idea that we have a closed interval that we're looking at. Now notice they also give you, we'll highlight the fact that this function, this quantity function E of t, is differentiable. So we're going to be able to use that to get our conditions that we need for our theorems. Now they gave us the values of E of t in hundreds of entries. Pay attention to that. This is 400 entries. This is 1,300 entries, 2,100 entries, 2,300 entries. So make sure that you're paying attention to the fact that those are hundreds of entries. So let's look at part A. So part A, we're going to use the data in the table to approximate the rate in hundreds of entries per hour at which the entries were being deposited at time t equal to 6. So what you're saying here is what you need to be thinking is that what you're trying to do is approximate E prime of 6 because it's instantaneous because we're at time t equal to 6 and we're going to approximate that. Remember, this is the slope of the tangent line, and to approximate that we have to use the average rate somewhere around 6 that we're doing it. So we'll have to pick some values. 6 is between 5 and 7. So I would say I would use the average rate of change in E in order to calculate an estimate for E prime of 6. Make sure you show your computations. And remember this one, you have to show your difference quotient as you're doing it. All right, now let's go to B. So the first one's fairly easy. And I would make sure that you go ahead and just write the sentence that goes with it to interpret that rate after you get it. Now in B, we're going to use a trapezoidal sum. So in your head, you got to remember you're doing the left sum plus the right sum and then averaging them, so dividing by 2. We're using 4 subintervals, so we will pay attention to that. We're using the table values to approximate. Now notice, however, you're not approximating only the definite integral, you're approximating the definite integral with this constant in front of it. So I would like you to think about, based on the notes that we just came out of, what is this actually approximating? So interpret that in terms of what it's approximating. And notice that what they've said here is that you have to have correct units and you have to explain the meaning of this in terms of the number of entries. So you want to think about the unit that we just came in and interpret what this definite integral with the constant in front of it means. What does this adding the 1/8 in front of it mean to interpreting the problem? Okay, and make sure that when you look up here, let's just check real quick. We're doing a left and a right, and we're doing 4 subintervals. And we do have 1, 2, 3, 4 rectangles that we're going to use. Please check your delta x and see whether or not your delta x's are the same for everyone or if they are different when you're doing that. So be careful about that and showing your work. Okay, so we have that one down. Now let's take a look at the next one. At 8 p.m., the volunteers are going to begin to process the entries. So up until 8 p.m., we've been putting entries in the box, and we're using E of t as our function to designate how many entries are in the box. But now, once we begin to process the entries, that means that we're going to be taking entries out, okay? We're going to be taking entries out. So they're processing it following this function right here. And notice they even give you units. It's hundreds of entries per hour. So this right here you have to recognize is a rate function. This is how much entries are going out of the box per hour. So that's a rate function. And then the question is, how many entries had not yet been processed by midnight? So in other words, they're asking, what is the amount that is left in the box at midnight? And so where I am, let's remind you, how much I have at midnight will be how much I have when I started processing. Okay, so you might want to think about, how many do we have when we started processing? We started processing at 8. How many hundreds of entries were in there? 23. So we'll take the E of 8 that we've had, and then we need to take out, okay? This is how many we're processing, and processing means take out. You're going to take out the net change between 8 and 12. And I'll let you figure out what should go in this position right here because of that. And then in D, according to the model from part C that you're creating, so that means you should probably come up with a function for this. I did it as a specific E of 12, but maybe you want to write this as the amount of entries in the box at X is going to equal, and then what formula are you going to write for that? And then we want to determine when they're being processed most quickly. Most quickly. Now you have to think about, yes, this is a max or a min. It's an EBT because we are on a closed interval, even though it doesn't re-reference it here. We are on that closed interval from 8 to 12. And so the question is, what is this the max of? What is this the max of? You may not need E of X for this. You may not be using E of X at all. You need to think about what function are you trying to maximize here. All right, I'm going to pause this. I'm going to let you work the problem, do everything that you can, and then come back and check your answer. All right, so now we're back. We're going to take a look at our solutions for this. All right, so again, the first thing that we're going to look at is come down here, that our rate in hundreds of hours are E prime of 6. You want to make sure that you have shown that this is what we're approximating and maybe labeled it, because they didn't actually say E prime of 6. So the rate in hundreds of entries per hours at T equal to 6 hours. Here's my difference quotient. You can either have this or this. You don't need both. And then notice I put my answer and I put how many, what your units are. You can say 4 hundredths of entries per hour, or you could say 400 entries per hour. Doesn't matter which of these you put, but make sure you're careful about your units. So our when, our what, increasing, and how much, and units that are there, so that you have that. Okay, then we're showing our estimate for our 1/8 times our definite integral. So that would be 1/8 of our trapezoidal sum, the left plus the right divided by 2. I show my work for calculating my sums. And again, remember that your delta x's are different for these. So 2, 3, 2, and 1 are my delta x's, my width of each rectangle. So I've written them separately, and then my left endpoints, my left heights, and then I did my right heights divided by 2. This was, I believe, a calculator problem. If I did not say that, oh, it said calculator permitted at the top, so that was obvious. So we type it in and we get our 3 decimal answer. And I do want you, if it is a calculator problem, to make sure you write the answer correct at 3 decimal places. You do have to simplify in the calculator section. So that was the first part of B. The second part of B was to interpret what this is. Now, if that 1/8 had not been there, then it would have simply been the net change in entries being deposited in the box. But the minute I add that 1/8 there, then that is the average value of E of t, the average value of E of t. Now, one of the things that is commonly missed on this is the units, which I'm coming back up here to talk about. Now, when you are doing this net change right here, this net change is going to be hundreds of entries times your hour. That when you're calculating this, the net change in the entries that are being deposited, you kind of like get confused a little bit about your units. But if you understand that this is the average value of E of t, then this number right here should have units that match E of t, which is why the units are hundreds of entries there. So be careful about that and make sure you kind of pay attention to what units you would have. All right, again, for C, where I am is where I was plus my net change. So I had 2,300 at 8. That was what was in the box according to the chart above. And then I calculate this definite integral. Now remember, this is a calculator problem. So how did I calculate this definite integral? I put it in my calculator and I did function int on the P of t that they gave me. Do not be doing this by hand. If you try to do all the work to integrate that by hand, you are wasting time on the AP. And also, did I show that anywhere that I actually did function int? No, they don't care. They don't need to see calculator commands on the AP. You're going to do it, and you're just going to type in your calculator, and you're going to get the -16. And again, the units of this is how many entries are in the box. So it's 700ths of entries, or you could say 700 entries. It doesn't matter which one you do. All right. Now, what you're doing in D is we are trying to look at when the entries are being processed most quickly. Not when the amount in there is a max, but when they are being processed most quickly. So we're trying to look at P of t, and we want to maximize P of t on the closed interval, which is why that we're doing EVT. P of t is continuous because it was polynomial. That satisfies the requirements for EVT. We probably should have said on the interval, we're on 8 to 12 because it's a polynomial. Our critical values are when the derivative of P of t is equal to 0. All I did on my calculator was I used nderive. You don't have to tell them you use nderive, you just do nderive. And then second calc 0 and get this value. You put this up here, okay, and then you make sure you check your chart. So I plugged in P of 0, I plugged in P of this number, I stored it on my calculator, plugged it in and got this, and then I plugged in 12. And so the entries were being processed most quickly at t equal to 12 at midnight because this was the largest. Make sure that you are not using a first or second derivative test justification over here. Use EVT.